So last time we started this example, we didn't go much through it. We just did the small eccentricity. And by definition, small eccentricity is when the eccentricity on the column ranges between 0 inches all the way to 10% of the depth edge. Now, which one is going to be the depth edge in this case? This is going to be the question. If the moment is happening about this axis, y, the moment is going to be causing here, let's say compression, here's going to be tension, and in this case, the depth edge is going to be 20 inch. But if the moment is going to be about the x-axis, causing compression on the top and tension on the bottom, the depth edge now is going to be 14 inches. So I hope that this here clear to us. So to do this, if I may go quick through the example again. So first we have the cross-section area of the column. You have 14 by 20, and total steel cross-section area is going to be 6 times 1 because I have here 6 number 9. For 1 number 9, you have a cross-section area of 1 square inches. So in this case, I have total of 6 square inches for the steel. Now, when I have a small eccentricity, I can use this equation safely. This equation, again, this is the one that we used when we consider a column exposed only to an axial load. It's going to be the same equation. I have the phi factor is 0.65, as we all know. This 0.8 here to account for the small eccentricity. So this kind of a reduction from whatever the column is going to be able to take, just because we know that each column should have some little bit of eccentricity. This term here is to account for this concrete contribution in strength. As it says here, 0.85 F prime C, and then times A sub G subtracting AS. Now this is going to be the steel contribution, the vertical rebar, so it's going to be 60 F sub Y multiplied by 6 square inches. With this, I have a total of 672. So this 672 represents the axial load that this column is going to be able to support in case of you have no moment at all, or you have a small moment of a small eccentricity. The small eccentricity in this case is going to be equal to 10% of, if I may put this here, I'm going to say here, for 10 inch, 20 inch for the depth, total depth, 10% of it is going to be equal to 2 inches. And therefore, phi min is going to be equal to the axial load. Where's axial load? Axial is going to be phi Pn multiplied by 2, which is eccentricity, divided by 12, put it in feet. So this moment here, if you like to look at it, here's the moment value is going to be 10%. This is going to be the eccentricity of the depth edge, the 20 inches, multiplied by 672, and with that I'm going to have 112 kip foot as a moment. Meaning, this column is able to support a total load of 672 with an additional moment that goes from 0 to 112 kip foot. So again, as long as the moment applied on the column is somewhere between 0 to 112 kip foot, your column here is able to support 112 kip foot and an axial load of 672 kips. Are we good? Any questions? Yes? No?
We're good.
We're good, thank you.
All right, great. Now, the second item, which is B, it says here, solve this problem when E is going to be equal to 5 inches. So now I know the amount of this eccentricity, but I don't have the axial load and I don't have the moment. But all what I know that the moment is going to be equal to axial load P multiplied by this E, the eccentricity, like what we are looking here at. Because this moment is going to be equal to P multiplied by E, the eccentricity. So I said, okay. Now let's consider here that E is going to be equal to 5 inches. Now, how can I solve this problem? What is the information available and what is that I need to work on? Now, as long as this PU is going to be very close from the reinforcing bars itself, I can assume here safely that the compression steel is going to be yielding. And this is exactly what it says here. Epsilon S prime is going to be more than epsilon Y, which means the compression steel here is yielding. And it's going to be okay to assume that the compression stress in the steel here is going to be equal to F sub Y. So this assumption is valid. Kind of, yes, I know it because I solved the problem before. And I know how it's going to look like. Now, epsilon sub S is going to be the tension strain in the steel. If this tension strain in the steel is going to be lower than the yield point, it means the stress in the steel in tension is going to be lower than F sub y. Now, what's the relationship? Again, I'm going to say if you take the strain in the steel multiplied by E sub S, you will get here to F sub S, which means the stress in the steel, the tension steel. And at the end, the tension force in the tension steel is going to be equal to the stress in the steel multiplied by the total cross-section area of the steel in tension only. Now, I don't know what happened when I jumped this way. All right. So in this case, I'm going to be taking this axial load, which in this case is going to be Pn. I can just say phi Pn, but I don't have the phi factor yet. And also, when you look here at the forces that I put here, this is going to be the standard forces that we usually put on a column or on a beam. We put compression force, another compression force here for the compression of the steel. This compression force C sub 1 is going to be on the concrete, and then you put this tension force. If you recall here, this tension force is going to be equal to AS multiplied by F sub S. You understand that? It means the phi factor is not there yet. Otherwise, you'd have seen here phi Tn, but we don't do it this way. When you put all of these forces, we do not include the phi factor in there. This is the reason, if you'd like to put here this axial force on the column, you need to put it as Pn and not phi Pn. Otherwise, this is not going to be consistent analysis. So, okay. So here's Pn is going to be at eccentricity of 5 inches. So I'm going to say, I understand this is going to be the phi, the E factor, which is eccentricity in terms of inches. I'm going to say E equals to 5 inches. Now I'm good about this, right? I know this is going to be the eccentricity, which means now the moment acting on the column is going to be equal to this Pn multiplied by this E. Great. How about now, how many forces do I have acting on this concrete section? I'm going to say I have total of 1, 2, 3, and 4. In the past, I didn't have this Pn, I just have a moment. Now, in this case, I have 4 forces. This force here, P sub n, is going to be like external force applied on the column. And the internal forces is going to be the 2 compression forces in the concrete and the steel, plus the tension in the tension steel. So all of this is going to be now internal forces, and this is going to be an external force. Now, when it comes to the strain, understand on the top, concrete is going to be failing at 0.03. This is going to be the capacity point. This is going to be the strain at which we do our calculation for the capacity of this concrete section. The depth of the neutral axis, it is the same, the standard that we quote here, C lowercase, while A compression depth, the compression block depth, which is equal to 85% of C. This happens when the concrete strength is 4,000 psi. If you start here to add more trends to the concrete, this number here is going to drop down. The beta 1, if you guys recall the chart, for each additional 1,000 psi, you're going to have a drop of beta 1 of 5%. Is it okay? So now understand this A is going to be the compression block depth, and C is going to be neutral axis depth. The strain in the tension steel is going to be equal to epsilon sub S, while in the compression steel is going to be epsilon S prime. Okay, good. Now, I can find out an equation for C1, and this equation is going to be simple. It's going to be the compression of the concrete. Compression of the concrete is going to be equal to 0.85 F prime C multiplied by the depth A multiplied by the width, and the width is 14 inch. Okay, I guess we should be able to write it down. Here it is. But when it comes to A, I'm going to say I understand that A is going to be equal to 0.85 times C. Why would I do this? Because before I start, I need to look at my unknowns. Unknowns in this case is going to be the strain in the compression steel, the strain in the tension steel, the amount of force that we're talking about, and C. The easiest way here is try first to solve for C. So everything that you're going to be writing here in terms of the force, try to put them in terms of C. You simply do this because if you solve C, you're going to have a good idea about the strain in the compression steel from the symmetry. You know that this here is going to be 3 inches, and once you know C, you can find out the compression steel strain. And once you have it, you can also find the tension strain in the tension steel. Now, once you have all of that, it means that now you have all the forces. If you have all the forces, now you can solve for Pn and Mn. In the past, when we used to solve only for beams with no axial load in the concrete section, we didn't have this Pn, and we have only one unknown or one target that you're trying to do, which is Mn or Phi-Mn. Now I'm gonna have here Phi-Mn and Phi-Pn. But the good thing about this, that they're related to each other. Because I'm gonna say here, Phi-Mn is gonna be equal to E, which is 5 inches, multiplied by Phi-Pn. So if you solve for Phi-Pn, now we have Phi-Mn. So actually the two unknowns here that we're talking about, the Phi-Pn, Phi-Mn, very related to each other by a factor of 5 inches. So this is gonna be simple. So again, I'd like to put everything here in terms of C, the depth of the neutral axis. So you can say here it is. C1 is gonna be equal to 0.85 times the concrete strength times A. And how much is this A here? I'm gonna say A is gonna be this 0.85 times C, which is beta 1 times C. Times 14 inch. What's 14 inch again? It's gonna be the width of the concrete section. So now I have the first compression force is equal to 40.46 times C. So it's gonna be constant times neutral axis depth. This is the first force. How about second force? Second force is gonna be the compression and the compression steel. And how much is this C sub 2? Let's say we assume that this epsilon prime S is gonna be equal to the yield point, and therefore the strain in this compression steel is gonna be equal to 6 kSi. Now here's C sub 2 is going to be equal to F sub y times A prime S. So you have 3 number 9. If you say here 3 number 9 is going to be 3 square inches times 6 is going to be 180 kips. But all of a sudden here, I see a new method of doing this. You subtract here this area of the steel multiplied by the concrete. The reason is because you don't want to do an overlap between the concrete and the reinforcing bar cross-section area. So some people in the past, when we were doing this analysis, if you recall, we just ignore this piece here. You can just ignore it if you want to. But here is going to be kind of sensitive, and look at the sensitivity here. If you look at 3 times 6, it's going to be 180 kips, right? Now compare 180 kips versus this detailed analysis, and you're going to be getting 169. This is not a small percentage. If you think about it, it's like 5%. You shouldn't be ignoring it. So actually, this is going to be a kind of a more detailed method of doing it when you have compression steel. So again, when you have compression steel, you should subtract the cross-section area of the concrete that you have considered in here. Because look at this C1. When you look at C1, it includes the entire cross-section area exposed to compression, which means this cross-section area here, right? And this equation says 0.85 times 4 times 0.85 times C, which means this depth, right? Multiplied by 14 inch. So it takes the entire cross-section area. And then when you work on the steel, right, you consider the same cross-section area. So you double count the cross-section area of the steel. So the easiest way is subtract the cross-section area of the steel out of this equation here by multiplying it by the concrete strength. Someone's gonna say, why don't you reduce this C1? But if you reduce C1 by this cross-section area, you're gonna be in trouble because this C1 is not gonna be in the mid-height of this A. It's gonna be shifted a little bit down. So you don't wanna go through this hassle. It's just easy or easier if you just subtract the cross-section area of the compression steel multiplied by 0.85 A prime C. Instead of subtracting it from this C1 equation. So now I ended up with numerical value for C sub 2. Now how about T? You see, well, the tension force now, this is gonna be trouble because I don't know exactly if the steel has been yielding or not, but I know it may not be yielding. And in this case, I need to have T in terms of C's. So now let's go here to the next slide. We know this equation here. The tension force is equal to the cross-section area of the steel multiplied by F sub S, which means equal to the strain in the steel multiplied by ES multiplied by AS. Nothing here new because of this fact. So now this is clear, very clear to me. Tension force is going to be equals to the strain in the steel times ES times AS. Now, I guess this steel strain here, if I'm going to go back, I can relate the steel strain in tension to relate it to the depth C, because I simply can say this epsilon S, you can divide it by D minus C. What is D minus C? The distance from here to there, right? It's going to be equal to 0.03 divided by C. D minus C, I know the depth is equal to 14 plus 3. Now we are talking about the depth. Now where's the depth? From where to where? I'm going to say from here to there. And the depth is 17 inch. It's going to be right here, this number. So in this case, I should be able to find out T in terms of C's. And this is exactly what we are doing. Here's the relationship between the strain in the tension steel to the 0.03 compression strain in the concrete to D minus C divided by C. So we have it. We can put all numerical values. And for that, at the end of the day, I can find out that the tension force equals. Look at this equation now. Tension force equal is going to be equal to 261 multiplied by 17 minus C divided by C. Someone's going to say, where'd you get this number from? The 17 C divided by C. I'm going to say, you can just simply go through this. The strain in the concrete is going to be 0.03. ES is at 29,000. AS, I guess you can solve for it numerically. AS in this case is going to be only 3 square inches. Why 3 square inches? Because you're looking at the tension steel, not for all the steel in the section. So it's going to be only 3 square inches. And then clean it up, you're going to end up with this value here, 261. So now it's going to be an equation between T and between C. Now I guess you should be able to say summation of the force in the X direction equal to 0. Otherwise, this system or this section is unstable. What are the forces acting? And say, okay, let's look here at the direction of the forces. You can say Pn plus C1 plus C2 equals to T. All right, or you can say C1 plus C2 minus T is going to be equal to P. So, which is right here. So, okay, fine. Now put all of these components. C1, I have in terms of C. If you look here at this equation, here's C1. C2 is just numerical value. The tension force was also based on the C value. So what do you have now? Now I have an equation between two unknowns. The first one is called Pn, and the second one is going to be called C. So right now I have an equation between Pn and between C. So, okay. Can I just solve for it? I mean, is there another equation that I can use? I'm going to say yes. Why don't you take the moment about the tension force, about this point here, right here, for all the forces acting on the system? So in here, here's the first equation that we just done with, right? This is going to be the first equation from the previous slide. It's going to be this equation. I'm going to be taking the moment is going to be equal to 0 about the tension force T, about this rebar. Meaning, I'm going to be taking it here and also for this axial load component, the external force. So you can say Pn multiplied by how much? By 12, right? You say here Pn multiplied by 12 inch. How do I know that this 12 inches? You say I know the distance from the top rebars to the bottom rebars 14 inch. And this eccentricity is going to be equal to 5 inches from the center of the beam. So from here to there is going to be 7 inches plus 5 is going to be 12. Why this is 7? Because it's going to be the mid height of the cone. 17 divided by 2 is going to be 7 inches. You can say this here 7 inches. All right. So Pn times 12. Okay, here's Pn times 12 equals. You have here C1 times this distance from here to there. C1 times, if you like, call this Y1 plus C2 times Y2. How much is this Y1? I'm going to say this Y1 is going to be equal to the total depth subtracting A over 2. This is going to be very similar to what we used to do the beam analysis, the simple beam analysis. This is going to be equal to the depth And how much is the depth again? That was equal to 17, right? 17 inches. 14 plus 3, 17, subtracting a over 2. Where's a over 2? Here's a. Why over 2? Because from here to there, because this compression force, C1 is going to be right at the mid-height of the block. So in this case, this 0.85 C divided by 2 is going to be in this equation like this. So, okay. Now let me try to understand this. I'm going to say this term is D minus A over 2, which is this term here. And the compression force C1 is equal to 40.46 C. Where does this come from again? I'm going to go back here. I'm going to say it's going to be right, this one here. Because C1, I have it in terms of C, and C2, I have numerical value for it. I say, okay. So now I'm done with this term. This is going to be C1 times Y1. And then says here plus C2 times 14. Yeah, it makes sense. Here's C2, the compression force on what? Is given the compression steel. And the distance from tension steel to compression steel is 14 inch. I say here's the 14 inch. Now I know where this is coming from. So this here term is going to be the C2 multiplied by 14. All of this is going to be equal to Pn times 12. So what happened to the 12? I brought it here on this side. So someone's going to be looking at this and say, is this to convert something from feet to inches? I'm going to say, or inches to feet. I'm going to say, no, this is just this 12 that used to be in this side. I just brought it here on this side in the denominator. So, okay. Now, what do I know about this equation? This equation here, it shows me a relationship between Pn and between C. And the rest of it is going to be like numerical factors, right? Numerical values here. How about in this equation, second equation? Same thing. I have here Pn, and also I have in terms of C. Again, twice. That's right here. I guess I should be able to solve 1 and 2. When you solve 1 and 2, here is C. C is equal to how much? 14.86 inches. How do you find out Pn? I'm going to say, just go back to equation 1 and use C of 14.86. This is what you need to do. Substitute here, C is going to be equal to 14.86. Once you do this, you can find out Pn of 773 kips. Now I have the axial load. Let me remind you with what we're after. We were after phi Pn and phi Mn. So now you need the phi factor. Which phi factor should I use? Are you talking about the 0.65 or are you talking about the 0.9? I'm going to say it depends on the strain and the steel. So now I need to go back and confirm the strain and the steel. I'm going to go back here one slide to show the equation that we use for the strain. Here is the strain and the steel. The strain in the steel is going to be by symmetry or by this two symmetrical triangles. I know that the concrete strain is going to be 0.03. I have the depth, the 17 inch. Now also I have the C, which means now I can solve for the strain in the steel. So, okay, here's the strain in the steel. I can solve for it. It happens to be 0.0043. The yield point is 0.002. So I'm going to say, what is that number that you're talking about here? I'm going to say this is going to be the strain in the steel at the yield point, right? What is that? So I'm going to say this is going to be the strain in the steel at the yield point. So just want to be sure that we're clear on this value, where it's coming from. So it happened that the strain in the tension steel is lower than epsilon sub y, which means steel is not yielding. So in this case, I guess if you look at the chart for the phi factor, it's going to be 0.65. Now, how much is phi Pn? This is going to be the one that I use in my design. The phi Pn is going to be 0.65 times the Pn, the 773, 476 kips. How about the strain in the compression steel? Because let me remind you here with the assumptions, if I may go back. First assumption, the steel in tension is not yielding, which is true. But I have another assumption here that I start with. I said that the strain in the compression steel is going to be going beyond the yield point. Now, is this true or not? Otherwise, the entire solution is going to be bad and I need to redo it again. It's going to be lots of work. So let me here, if I move forward, let's here try to find out the strain in the compression steel. I guess you guys are familiar with this equation. Also, I'm going to go back here to look at the strain distribution. How do you find here the strain in the compression steel? How do you find this? You say this epsilon S prime, if this divided by C minus, how many inches from here to there? Yeah, say 3 inches. So if you take the strain in the compression steel divided by C minus 3, it's going to be equal to 0.03 divided by C. Now we have the numerical value for C, so I should be able to find out the strain in the compression steel. All right, we did it. Okay, here we go. C minus D prime. This is a C minus 3 inches divided by C, multiplied by the concrete strain. Well, it is more than the yield strain, which is good. The assumption was good. So now I have PPN, but I don't have Pman. What's the relationship between PPN and Pman? Anyone recalls? Yes.
Time PPN.
Say it again. Who is this? Ramin?
E times PPN.
All right, Ramin. All right, so let's check this out. Pman equals PPN times E, and your eccentricity is only 5 inches. So you take the PPN, multiplied by 5 over 12, it's going to be 198.3 kfoot. This means this section here, concrete section, is able to take this axial compression force, which is 476. As long as the moment value ranges from, the applied moment ranges from 0 to 198.3. This makes sense to you guys? All right. Let's move here to the third point on the problem. So I'm going to go here backwards. I need to look for C. What does it say? It says C, the balanced strain condition. So you need to find out PPN and Pman, at which the balanced strain condition or compression controlled strain limit, when the steel, the tension steel, is going to be at a strain of 0.02, which means it's going to be right at the yield point, and the concrete is going to be also at 0.03 as usual. So okay.
Professor, so it's saying find the strain condition at where C would be?
It says here, if you remember the problem, it says find the design axial load strength, PPN. And of course, it's going to be the Pman. You can do it with it, right? All right. When, item C, at the balanced strain condition. What's the balanced strain condition? Or compression controlled strain limit, at which the strain in the tension steel is equal to 0.02. Make sense or no?
Yeah, okay. Thank you.
Let me open this slide for you. Yes, say, let me go here. Old slide set, rectangular section. Gonna be going to our nice chart here. This is what you call here compression controlled performance. It's gonna be tension controlled performance. It's gonna be the transition zone. The limit in the tension steel in terms of strain for the compression controlled is 0.02. So at this point, the steel is yielding. So when the steel is going to start to yield, right, it's going to be the point at which you're going to be leaving the compression control to the transition control. Once you reach 0.05, now we're going to be in the tension control. Let me take you back here. It says find out Pn, and of course Pman that goes with it, at the balanced strain condition. What's the balanced strain? It happens when the compression concrete is going to be exposed to 0.03 and the tension steel is going to be right at the yield point, right there. It is also called the compression controlled strain limit when the strain in the tension steel is 0.02. This is true. Here's the limit. 0.02, the tension steel. It's going to be at this strain value. I hope this is now clear. So item C, section C of the problem, it's going to be the balance condition. So the balance condition, what happened? It's going to be a unique point. It's going to happen when the concrete compression strain is going to be 0.03, which is a standard. This is going to be the failure point or capacity point. And the strain in the tension steel is going to be the yield point, which is 0.02. Now just imagine if you have here grade 75. So if you have grade 75 steel, this point is not going to be 0.02. It's going to be 0.025. Am I correct? Does it make sense? You say yes, because this is strain value, the 0.02. It happens only for grade 60. When you look at the equation, say it's the strain in the steel, right? It's going to be equal to the stress divided by E. And the stress in this case is going to be equal to 75 KSI. This is provided if, for another problem, or maybe an exam problem, or maybe a quiz problem, that I give you the grade of the steel to be 75 KSI. Are you guys following me? Yeah or no?
Yes.
Okay, good. So this here, the balance condition. Please keep in mind this. Remember this, the balance condition, the term balance condition. So later on, if you see it, you're not going to see what is the balance condition. So here's the balance condition. Let me put this here, a box, little box around this. Balance condition happen. Concrete strain is going to be 0.03, and the tension steel strain is going to be at 0.02. It's going to be right at the yield point. Okay. I guess this problem should be so simple, because usually I used to say, I don't have the strain in the steel, or I don't have this C. Now I guess finding out C is going to be simple, because I have the total depth is going to be 17 inch, the depth of the beam from the compression to the tension steel. And on the top here, I have 0.03. At the bottom, I have 0.02. It's going to be so simple to find out CB, because I can say 0.03 divided by CB. Why would you call it CB? Just used to be C. You can say, yeah, this is to indicate this is going to be C balance. But in your analysis, you don't really have to call it CB. You can just call it C if you want to in your analysis, right? So you can say 0.03 divided by C is going to be equal to 0.02 divided by D minus C. You have here one unknown only, which is a C, because the depth you have it at 17 inch. Here's the equation. 0.03 divided by C is going to be equal to 0.02 divided by 17 minus C. Now we can solve for C. It's going to be 10.2 inches. Now I have this. I guess the rest problem is going to be so simple. Now you need to find out the strain in the compression steel. How would you do it? Very similar to the previous problem. It's going to be 0.03 divided by C equals the strain in the compression steel divided by, you can say C minus, can someone help me? C minus what?
A prime.
Which is 3 inches in this.
3.
Okay, here's the strain in the compression steel. Look at this, 0.0021. It is right there. It is almost at the yield point, right? So I'm going to say now, yes, the compression steel also still yielding. So this is good. Yeah, make our life easier in our analysis. I guess now I should be able to find out numerical values for T and C1 and C2. How is that? You can say you have the depth A, because A is going to be 0.85 of this. So you say here A times 0.85 A prime C times the width. This is going to be the compression force C1. How about C2? You say C2 is going to be equal to 3, because I have 3 bars. Each one is going to be 1 square inch multiplied by 60. Why 60? Because the compression steel is yielding. How about the tension steel? I'm going to say tension steel is yielding. According to my assumption here, I'm solving when the steel here starts to yield in the tension. I'm going to say this tension is going to be equal to 180 kips. 3 times 60. Okay, now it's going to be so simple. Now I have the 3 forces. Here's C1, C2, and the tension force. Here's C1, C2, and tension force. Now I still have also this axial force. It happens at some eccentricity. They still call it also EB. In your analysis, it's okay to call it just E. It's going to be okay. Now we can do summation of the force in the x direction equals 0, right? And in this case, you say C1 plus C2 minus T is going to be equal to P sub B for the balance, or Pn if you like. Look at the equation here. This P is going to be equal to these 2 forces minus T. You have numerical values for all of these internal forces. So the P here, the axial load, is going to be 403 kips. This is going to be Pn. How about the moment? Moment, you're going to say moment equals this Pn multiplied by this eccentricity. Do you know how much is eccentricity? You don't know it. So why don't you again take the moment about this point for all the forces, and also about this point? So you can say here, Pn multiplied by EB plus how much? Can someone help me here? How much is this? Yes?
7 inches, right?
Yeah.
Yeah.
So it's right here. Look at this. E plus 7 inch. Look at this. E plus 7 inch multiplied by this P equals C1 times the distance from here to there is going to be D minus A over 2 plus CT multiplied by 14 inch. Where is the 14 inch? Can someone point it to me, please? Where is this 14 inch coming from?
From the top and bottom of the rebar.
Oh, you
Or
mean
the
from
distance
here-
between the rebars.
from here to there, right? Exactly. Yeah, because you take the moment at this point, so you take this C2 multiplied by 14 inch. Now, out of this equation, you have P already because we solved already for Pn. So in this equation, what is the only unknown that you're looking here at? This now you have this numerically. Look at this equation. It's going to be E. That's it. Now we have E. Take this E multiplied by phi Pn. Now you tell me what phi factor should you consider here? How much is the strain in the tension steel? I guess that was actually given to me in the problem. I don't have to recalculate it. It was given to me to be at 0.02. The question asked me to find out phi Pn and phi Min right at this point when the tension steel is going to be at 0.02 strain level. I said, okay, it means phi factor is 0.65. Okay, good. So phi Pn or phi Pb, if you like, is going to be equal to the phi factor 0.65 multiplied by Pn to 403, taken from here. And phi Min, all what you need to do is just multiply by E, take this number here, right? Multiply it by E, and then divide by 12 to put it in kip-foot. So what does it mean by these two values? It means this column is going to be able to support 262 kips as long as the applied moment on it ranges from 0 to 259 kip-foot. If you increase the amount of applied moment beyond this point, this column is not going to be good. So, okay, this is good. I guess I'm done. Now I need to understand these points. What does it mean by these points? All of the work that we have done. You can say, here's the first point. PPN, based on the simple equation. Someone's going to say, which simple equation? I'm going to take you back to it. I'm going to say, okay, this is going to be the simple equation for compression. Remember, assuming that you have a small eccentricity, is going to be 672, and then you multiply by this is going to be the PPN. And the amount of moment that goes with it for the small eccentricity, when you have the maximum moment, is going to be equal to 10% eccentricity multiplied by this axial load. And we say it's going to be 112 kip-foot. So, okay, where is this point here? 672 and 112. I'm going to tell you, okay, let's go here, move forward, and look at the interaction diagram and try to understand where this happens. Here is the axial load value that we just talking about. This is the one that we just calculated out. So, okay, here's this point. How about when you say here with the small eccentricity? Small eccentricity means, or is going to be 10% of H, and actually this is going to be this point. Therefore, the moment is going to be right here, which is 112. It's going to be right here at this point. So I guess now we understand this point and that point. Am I correct? Any questions on this? So I'm done with this section of the graph. Yes or no?
Yes.
Amin? Amin? Mr. Amin, are you there? Anthony, are you there?
Right here.
Okay, Anthony, thank you for answering. Anthony, I'm just wondering, where did they get this moment from? Do you know? This moment value. Is the moment on the x-axis or the y-axis? I mean,
X-axis.
okay. Where did you get this value? How did you solve for it? If I give you here phi Pn and I give you the concrete section, can you figure out phi Mn that goes at this point? And how?
Yeah, I don't.
Anyone else? Thank you, Evan.
You just multiply by E.
Or divide.
Please turn your mic off if you have someone next to you. And my advice, if you just move to maybe a different area at which you can listen and get the benefit out of this time that you spend here. All right, now who would like to answer me? Abigail, you think you can answer me on this?
Yeah, so to find the moment, you'd multiply the VPN by E.
And how much is E in this case?
E in this case is the, is it
You should
5?
be able to see it right in front of you.
11.88.
Where did you get this from? I'm talking about this point. I'm not talking about this. I'm talking about this point here.
That's 0.1.
That's
What?
going to be 10% of the H.
Who said this point one? Who said that?
Eric,
Eric. All right, good, Eric. Okay, stay with me, Eric. Cortez. What do you mean point one?
the 10%, the H for E.
And how much was H value in this case?
Didn't we get 5 inches?
It says here E 5 inches. Do you see this hand or you don't? So actually you have all the solution in front of you. So even if you're not giving enough attention, you should just be looking here at what I'm talking about and this red box and try to answer me. I guess, if I'm not mistaken. How much was the E that was considered in determination of this moment value? Anyone knows?
2 inches.
2 inches, why? Where did you get this from?
It's 10% of our base, which is 20 inches in this example.
All right, good. So I'm gonna go back here. Thank you, Tim. So I'm gonna go back here and look at this 10% thing. Where is this 10% coming from? It says here, when you have a small eccentricity, you can safely use it when the small eccentricity goes from 0 to 10% of H. And they said that you can just use this equation here and get 672 kips. I'm gonna write it down, 672 kips. And the moment that goes with it is gonna be equal to 672 multiplied by the 2 inches. Where's the 2 inches come from? It's gonna be 10% of the depth H. This is now our depth H times 2 inch divided by 12. It's gonna be 112. Gonna move forward here to my chart. I'm gonna be looking at this. I'm gonna say, this is true, like the number I have put there, 672. You see this? Over 600, maybe 672. Here's the 700 right above it. And this moment value goes to 112. It makes sense, yeah. So this is gonna be the point that we were talking about for the most interesting. Are we good now?
Yes.
Amin, are you there, Amin? Amin. Okay. Amin, are you there? All right. So that was the first point. So this area here is covered. Now I need to look for other sections. You see, the other section is gonna happen, if I'm gonna go here to item B in the problem, it says when B equals, when the E equals to have 5 inches. So you say, okay, let me now work on the 5 inch. How much was the moment? How much was the axle load? I'm gonna go here to B, right? This one we went was 5 inches. And how much was the moment? How much was the axle load? I'm gonna go to it, right? Coming close. Here is Pman. So Pn, if you like to write down these two numbers, 476, and let's say about 200 kfoot for the moment. So, okay, now let me check this point here. Let's give me this point here. Look at the axle load. How much is axle load? The numbers Our analysis says 476, and the moment is gonna be about 200. Look at this moment, about 200, right? Like 198, 200. I said, okay, good. Now I understand this point. So I guess between this point and this point, I should be able to connect with a line. So now I hope that you guys are clear on this line, right? And on this line. I'm doing here points on the interaction diagram, connect them with lines.
So just to clarify, the flat line is what we said was is the point. Excuse me, sorry.
Flat line, this area here, this section
Mhm.
was the small eccentricity.
Right, small. Okay,
Yes,
and then this other line that we're connecting from the minimum eccentricity to
this is
the 5.
just
the-
an arbitrary point that we picked 5 inches. Someone else could have picked 6 inches and find another point here or there, right?
Oh, okay,
And just connect to it.
got it. Thank you.
No problem. Now, the last item that we discussed, we said is going to be right at the compression controlled limit. What's the compression controlled limit again?
I think it was 0.002.
0.002 at the strain in the tension steel. So, okay, so what happened with this? Let me look here at this. We said that axial load, this is going to be the 0.02, the balance point, right? End of transition zone. 262, and the moment is, this is a moment, which is phi times E, phi PN times E is going to be 259. Now let me look at this. It says this is when the strain is going to be 0.02. This is going to be the transition point. Look at this. 259, 260, about roughly in this region. And look at this. How much is this? 262. Because this is going to be the 300, right? So now understand this.
262. Oh, okay, okay.
This is
The
the 300.
259 is the moment. The 262 is the axial.
262, yeah, 259, close to each other. So what I'm trying to say, now I understand this point and the significance of it. This give me the balance point. So I'm going to connect between this point and between this point. I'm going to say, okay, this is good. So what does it mean by that? It means if I'm going to draw here a line like this, right? I'm going to say this side here and this side, right? I have the strain in the tension steel is going to be less than 0.02. You agree with me? If the strain in the tension steel is going to be less than 0.02, it means that I'm at, if you like to call it this way, I'm going to be at, anyone can tell me if the strain in the tension steel is going to be less than 0.02, you're going to be at
Compression control.
compression controlled. And once you go here beyond the compression control, there's going to be transition. Once you get to 0.05 in the tension steel, is going to be what? Tension controlled. I said, okay, so the strain here is going to be 0.02. So therefore, this side here is going to be compression controlled. Because if you remember, when I did the analysis, when E is equal to 5 inches and E is small eccentricity, the strain in the tension steel was less than 0.02. I can go back here and prove it here. I can show it to you for quick. You can say, look at this. This is going to be what? The strain in the steel. Here is the strain in the steel. Here is Fs 1253, which means the strain was much lower than the yield strain. And here's the value. That was the strain in the tension steel, and that was the yield strain. This is 0.04. Now let me move forward here to the chart. I'm going to say, which means at this point, the strain is equal to 0.0004. So in this side here, the strain in the tension steel is going to be lower than the yield point. And then this side, the strain in the tension steel is going to be more than 0.02, more than the yield point. Does this make sense or no?
Is this graph also like the other graph where if you go outside of where this line
Yes,
is?
yes. I'm
Okay.
going to be coming to this in a second from now.
Professor, for the balance strain, is it always 0.002 or does it depend like on what grade we have?
It depends on the grade. Very good question. Thank you for asking this.
So we just divide by 2900.
Yes, exactly. You take the grade divided by 2900. So what happened? The compression controlled, the strain in the tension steel is going to be lower than the yield strain, correct? And what happened? in the tension control or transition and tension control, I'm gonna say in this case, the strain here is gonna be more than epsilon y, if this makes sense to you guys. So now I know what's happening in this zone here and what's happening in this zone here. So okay, now can I continue my analysis? Which means can I add more points to do the analysis on? How many points did we do so far? Anyone recall the points? They say we did 3, A, B, and C, right? Where is A? That was A. A was this point, just connected flat. And here's B, and here's C. Am I correct? In this example.
Mhm.
So
Correct.
it means to me that I can extend it and add more points. Someone's gonna say, how about this point? This is the easiest point actually, when you have no axial load. So this is gonna be like a section with compression reinforcing, and you should be able to solve for this. And we have done this before, right? So I know this point is easy point. Why? Again, because the axial load equal to 0. So you're gonna be doing a section with compression reinforcing. This is all what you need to do. It's gonna be a simple problem here. Anyways, instead of asking you to do lots of work, we said, well, our interaction diagram is gonna look like this. Yeah, look like this. So we're trying to find out what happened at this point. You see this point here? This point, the strain in the tension series is gonna be 0.05. What significance of this point? I'm gonna put this here. What happened at 0.05? Now you become in the tension control.
Tension control.
So right here, you're gonna be in the tension control beyond this point, and between here and there, this is gonna be transition zone. This is why you see here, it's kind of weird because the phi factor is changing. You see here, if the phi factor is not changing according to this line gradually in this fashion, you wouldn't have seen this kind of pinching in the graph. You'd have seen something like this. This makes sense to you, right? So the reason that this is happening because the phi factor that we are using a phi factor that's changing. Phi factor is not constant. If you have a constant phi factor, you're not gonna see it doing this. You're gonna see here very smooth curve, right? So, okay. I hope that this chart here is clear to you, the significance of all of these points. And just, you know, if I give you a column like this and ask you a simple question, I'm gonna see here your axial load, the axial load that you have as P sub U, right? P sub U equals, I'm gonna put the number there, and now I'd like to hear from you, is this gonna be safe or unsafe? P sub U is equal to 600 kips.
Safe.
And M sub U equals, how would you know it's safe? Wait.
Oh.
Wait, don't rush. And M sub U equals, I'm gonna say here 200 kip foot. Is this a safe column or unsafe column with this two axial load and moment combination?
It's not
No.
safe.
Unsafe.
Why? Because they're gonna say, okay, here's a 600 kips, right? And here is M sub U of 200. I'm gonna put it this way, close enough. I'm gonna say, let's see when they meet. They meet right here. Outside of this interaction diagram, it's gonna be unsafe. And you know what happened in reality when we do an actual design? What we do, we put the column, and then we do the interaction diagram for our column with the given reinforcing. And then we have lots of load combinations, right? You guys are aware of the load combinations like 1.4, 1.2, and then we throw all the points there after we are done because usually we're gonna have a moment and axial load. So we throw these combinations in the software, and the software is gonna be plotting it for you. Once you see a point outside of this interaction diagram, you know that your column is not good. Does this make sense? So, okay. Now let's look at this for quick. What happens here? Here's the column. You remember this column? It was number 8, same column that we worked with before in 24 by 24 inch. We said, okay, here's a column. You can do this VPN, the one that you're used to. It says here 1456. And then I put it through the software, and the software just give me all of these points. And just, you know, I can ask the software to give me up to 100 points, which means the software is going to pick lots of points and solve it for you, like up to 100 points if you want to. So in this case, I found out that maybe 15 points is good enough for me. So this is actually an output of a software. So what we usually do, we do P sub U and M sub U, and just we give it as load combinations and we throw into the software, and the software is going to give you circles like here and there and everywhere, right? I'm going to be asking a question to one of you guys. What is this point about? What do we call it? I'd like to ask Alan Bond. What is this point about, Alan? Alan? Alan Bond? Are you still here? All right, let's ask here Alfred. Alfred. Yes, Alfred, you are here with us.
Yes.
What's the significance of this point, Alfred? What's happening here? Why it is doing this, or what? What do you call this point? Do you know? Does it have a special name?
I'm not sure.
You have all the slides on you, right?
Yes.
Can you go back, please, and look at it quick? See what is this point about, or what's the name of it?
I see that it's in the transition zone.
Where's the transition zone? The point itself is a transition zone?
No,
So what?
it's from the
So what's the
compression.
name of this point? Does it have a name?
That's
You can look at the screen, or you can look at your notes.
yeah.
What do you call this node, this point? Do you know?
It's where
Does
E
it have a
sub
name?
E is equal to 0.002.
Great. Okay. Does it have a name?
No, I don't know. It's where the balance strain condition.
Oh, the balance condition. It's right there. Excellent. Good.
Yeah.
Thank you. Thank you, Alfred. Stay with us, please.
All right.
So this gave me actually the balance point. I guess I should be able to connect it this way, right? Say connect it this way. How about this point here? What's the name of it? I'm gonna say this point. I'd like to check with Amin. Third time Amin today. Seems that he's not here at all. Ashley.
Hello.
All right. So what is the significance of this point? Do you know?
Is that once it starts hitting or it goes into the tension control, or?
Exactly, tension control. Thank you. Here's what happened. At this point, the strain is equal to the strain, the tension steer is going to be equal to, look at this. It's going to be this point. It's going to be 0.05. So the strain here in the tension steer is going to be 0.02, and here's going to be 0.05.
Professor, going back to that, so I see that those 2 points are really close to each other.
Yeah.
How would you differentiate both of them? Is it just because I see
what,
right there it says E sub t is equal to 0.04 and then 0.5.
Yeah, 2 points. They're right here next to each other. Which means along this line, if I'm going to go here to this guy, to this chart, I'm going to say from here to there, you have the strain in the steel going from 0.002 to 0.005.
4 or
5 is going to be at that point.
Okay.
All right. You guys remember this point? What is this about this point? What significance of it?
That wasn't that called I can't remember right now, but
okay, so what happened here? Can you explain it to me?
Yeah, the moments there's no moment, there's no load. Isn't it just kind of gravity acting on the column?
No load, but they're like tension or compression.
That's compression.
How about here?
Oh, tension. Sorry. tension. That's where phi Tn is equal to.
Do you know how to find out the tension force here or the tension value?
Isn't that the AS times Fy of T?
S times Fy? Is this what you're saying?
Yes.
No compression effect at all? No compression there?
No, because
No
it's
concrete?
tension.
What the concrete? Where's the concrete? What happened to the concrete here in this equation? Why the concrete is not in the equation?
Because it's in tension right now.
Yes. So what
Yes.
happened when the concrete is in tension? Is it cracked or still working with you?
It's still.
It's cracked.
Oh, it's cracked.
Gone.
Right.
Okay. This is the same chart that we used last time. Just explain what's happening here, right? Now I'm gonna look at this and say, what is this? I understand this.
I'm
trying to
guessing the
convince
other one was a
myself.
spiral.
Yeah, no, I'm convinced myself that this is giving the interaction diagram, right? That I understand it. So I'm gonna say, how about this? I'm gonna say no. Let's look first. It shows here phi mn in the x direction and phi min in the y direction. And they say that this is at the point of this number here. This is what we call here biaxial, which means that you can have mx and mn in the same time that you have an axial load. So in this case, you have a case that we call here biaxial moment or biaxial column, which means that you have moment in both directions. Just imagine the column that you were talking about. You have moment about x and also another moment about the y axis. So actually, we're going to have a surface like this. We call this interaction surface. Now you have here moment about the x, moment about the y, and then you have an axial load. The axial load above this level is going to be compression, and the axial load at the bottom, this piece here, is going to be tension. I guess it's going to be tough if you need to do analysis like this by hand, but the software can do it for you and give you also this graph. And if you give it a load combination like mx, my, and p as an axial load applied to the column, it can give you whether it's going to be within this envelope or it's going to be outside of this envelope. Which
So
is
this is useful for finding two moments, right? And the x
two
and
moment
the
and
y.
axial load, right?
Okay.
So can you explain me why do I have this flat area on the top? It's kind of like if you have an apple and then you chop the top of it, right? Why is this piece like flat like this? Why? What's going on? Because if you tell me here, what is that? I'm gonna say this is because the tension, right? It was much
Right.
smaller. How about this piece? Why it is flat?
So then that would be because of compression. But
No, I'm gonna take you here. Why is this flat?
oh, because it minimal eccentricity.
The small eccentricity, exactly.
Mhm.
This to account for the small eccentricity. I'm gonna say
Mm.
all of this because all of these factors that you are imposing and the phi factor. How about if there is no phi factor and there is no term here like this 80%? I'm gonna say you'll get a curve like this. You see how smooth? See here, compare it
That's
with this.
because of the constant phi,
Yeah,
right?
compare it with this. You see this? The effect of this because the phi factor is changing. And that's why we have this. And why in the top? Because I have this 0.8 factor for the small eccentricity. But if you run it without this factor, the 0.8, and without this phi factor change, you're going to be getting a chart like this. It's going to be very smooth, right?
Mm-hmm.
This chart, actually, this interaction diagrams, they're very good. I mean, you can use them for rectangular column or circular column if you like, or spiral column. And the good thing about them, that what you need to do, this kind of generic, it works for any column, right? So you don't really need to do it with the software. If you don't have an access to software, you can use this. Let me explain to you what is happening here. I'm gonna say, on this axis here, what do you see? It should be the axial load, correct?
Mm-hmm.
And then this axis should be the moment. But I don't see here a column size, and instead of say, this is gonna be equal to h. So okay, and it's gonna be equal to gamma times h. So the distance from center of the bar to center of the bar, I'm gonna call gamma sub h, gamma times h, right? So this gamma now is gonna be less than 1. And this chart here is made for gamma of 0.8. This chart gamma of 0.9. This chart is gamma of 9.
And gamma gamma's not representing the unit weight, right? It's or
No,
is it?
this gamma here,
Mhm,
look at this. Here's gamma definition. If this is H, it's gonna be gamma H.
mhm.
Okay, good.
Okay.
This is gonna be Pn, and this is gonna be E. It's interesting. This interaction diagram is good when the concrete strength is 4K psi and F sub y is equal to 60. Same thing. Same thing. Same thing. I said, okay. It seems that you have a book full of all of these charts. I'm guessing yes. It's from PCI and CRSI. This is like some organizations. They have their manuals or their books, and it's full of all of this interaction diagrams. So you can do quick analysis to it if you want to. Now let's see what else. What is this for? Why do I have more than one line here? Because it says it's gonna be for the reinforcement ratio, right? So this is gonna be for different reinforcement ratio. I remember that you say the column vertical C ratio goes from 1% to, anyone remembers? 1% to what?
8%.
8%, absolutely. Thank you. So for each one of these, you can have just a curve. How about if I have 1.5%? If you have 1.5%, just draw a curve here in the middle, right? Just draw a curve here to be parallel between these two. If you have 5.5%, just draw a curve right here. Okay. So if I have the steer ratio, I can find out the steer ratio, and this rho t is going to be equal to AS divided by AG, right? So it's going to be the steer ratio. So what do you have here on this axis? It says Kn, a factor called Kn, and it's going to be equal to Pn divided by F prime C times A sub G. So okay, yeah, this represents the axial load because it's going to be kind of normalized axial load. You take here the axial load divided by F prime C times AG. But the phi factor is not there. Don't forget, the phi factor is not included in here. That's why I don't see here the breakdown in here in this area. Look at
Could you
this factor here. Yes.
Could you explain that again? I didn't understand Kn. So
Kn, normalized axial load. Kn is like represents the axial load because is equal to Pn divided by F prime C times Ag. We call this normalized axial load. Let's see an example. Example would make it easy for you. Okay, so hold on. And then after this, we said, how about this Rn? This Rn represents the moment, right? And this is true. Look at the moment. What does it say? Moment equals Pn times E divided by something. So I said, okay, good. Let's see an example. Here's the example. And this is going to be a very good example that I want you to study because I'm sure it's going to be in your midterm or maybe a quiz. It's going to be something similar to this because what happened, I give you a column, give you the axial load, right? Give you the strength, give you all of that. I'm going to say how much moment capacity can this column be supporting if you have the axial load demand is going to be this much, give you all the material properties. Also, what I will do, I'm just going to give you one of these charts, right? Now you should be able to solve with it because now you have the concrete properties, the steel and the axial load on it. I'm going to be asking you for the moment acting on it, okay? So good. Reinforcing bars is going to be 7 number 8. This is going to be for the vertical rebars, right? So I'm going to say this is going to be the vertical rebars, these rebars. The tie is going to be 3/8 of an inch at 2 inches. The cover is going to be that much. Why do I need the tie and the rebar size? I'm going to say because there is this gamma h. Gamma h is going to be the diameter from the center of the rebar, right? So what you need to do is to find out this gamma h, right? And then you have h, and with that you should be able to find out gamma is going to be equal to this diameter multiplied by the outside diameter or the big.
So in order to get gamma h, we just say 15 minus 2 times 1.
We're coming to it.
Okay.
Absolutely, you are correct. Okay. We quote here ds. What is ds? Is the gamma h that we were just talking about, right? So in this case, how much is ds? You're going to say 15 minus 3 inches, 1.5 inch from each side, minus 3/8 of an inch, because you have from here 3/8 of an inch, from here you have 3/8 of an inch, minus 1 inch, because you have number 8, and then you have 1/2 inch from here, 1/2 inch from there. Here is the 15 inch. All right, big diameter. Subtracting 3 inch. What is the 3 inch for? You're gonna say the cover, right? Minus
Mhm.
0.75. What is this 0.75? I thought it's gonna be 3/8. I understand
is
3/8,
in
but you have
center.
2 times 3/8.
Mhm.
I'm gonna say this number here is gonna be 2 times 3/8, 1 inch. Subtracting 1, what is this 1? I'm gonna say 1/2 of this bar diameter from here, 1/2 from this bar diameter from here. So we can say diameter to the vertical steel is 10 1/4. How about gamma? The big diameter is 15. So if you take this 10 1/4 divided by 15 is going to be 0.68, which is your gamma factor that you need to pick a chart for, right? Are we good? So I'm going to be using
Yes.
gamma of 0.7. So when I pick a chart, I need to pick the chart that goes with gamma of 0.7. Great. Now I know exactly which chart to use. So okay. My
So
view,
we're using 0.7 because the 0.68 is the closest, right? So
Yeah, I mean-
what would happen if we chose like 0.8 gamma?
no,
No,
you
no.
get close to it. I mean, if you're gonna have different numbers.
Mm-hmm.
When you go to 0.8, you're gonna be having larger moment capacity,
Got it.
but you'd like to get to the closest one as much as we can.
Okay.
Okay. You know, for a spiral column that you're gonna have a phi factor of 0.75, right?
Mm-hmm.
And then you have P sub U. That was given to you in the problem. Now take this P sub U divided by the phi factor to get to Pn. Why? Because this chart is based on Pn, it's not on phi Pn, right? There's no phi factor here. Said, okay. So let me take this 720. Now let's see what I can do here. This factor K sub n, I need to find it out. And what is K sub n equals to? Pn, the 720, divided by F prime C, the 4K side, divided by the cross-section area of the 15-inch column. Here's the 15-inch column, is gonna be 176.7. My Kn here equals to 1.02, is about 1. So I'm gonna say, okay, here we go. I'm just gonna go straight. Now I need to pick the vertical C ratio. I'm gonna say rho sub t is gonna be equal to almost 3%. Where do you have this from? I can take you back and show it to you. Here is AS. You have 7 number 8 divided by the cross-section area is gonna be almost 3.1%. So I'm gonna go here to 3%. This one is what? 1%, right? 2%, 3%. So horizontal line, once it hit the 3%, I'm gonna go down to find out R sub n. How much is R sub n in your opinion?
0.075.
Yeah.
Or 0.075.
Now, this Rn equals what? Equals all of this. What information you have about this? I'm gonna say, okay, now
P of n, we have that. We have
here's
the
Rn, I have Pn, I have F prime C, I have Ag, I have H, the diameter. I can solve for E.
Mhm.
Take this E, multiply by phi Pn. Where's phi Pn? Here is the phi Pn.
What was R of n again?
What?
Or wait, did I say that right?
This
Yeah,
Rn,
R7.
it is like an indicator for the moment.
Okay,
Rn is equal to this. Now,
got it.
phi Mn equals phi times phi Pn times E. And here's E, 1.1 inch. So now I was able to solve for this point here, for this axial load, the maximum moment that this column can support is going to be about, let's say 50 kfoot. I guess I've taken maybe 5 more minutes beyond my lecture time. Thank you for being patient. If you like, you can leave. If you have any questions, stay around. And you guys have a good night.
Professor,
Yes.
can I do the makeup quiz? I came to the office hours on Monday, but
Yeah, I had someone at the time, and actually he was